Hello and welcome. So today we are going to discuss about the properties of the discrete Fourier transform, in which mainly we have to cover about the circular symmetry and circular shift and circular convolution. So many of the properties of the discrete Fourier transform, as you can see over here, that many of the properties of the discrete Fourier transform are analogous to those of discrete time Fourier transform. Discrete time Fourier transform, you have already studied about that. So the properties are approximately similar. Okay, so with a notable exception, there is one exception, that all shifts involved must be considered to be circular. Whatever the shifts are there, that must be considered to be circular. All right, you will understand. Let's start that. First of all, defining the discrete Fourier transform pairs, DFT pairs. What are these pairs? That simply xn, the sample xn. If you are going to take the discrete Fourier transform of this, then it will become what? You have already studied that. It will become x k. Okay, and likewise, if there is x1n, so discrete Fourier transform of x1n should become what? Capital X1 k. And similarly, x2 is another sample, and the discrete Fourier transform of this will become what? Capital X 2 k. All right, so just see the properties of this, in which the first one is symmetry. Now, what is symmetry? If you have already studied about that, then symmetry is simply if xk is something the discrete Fourier transform of any xn, then you can see this, that xk should be equals to what? X star of minus k n. Okay, this thing. Simply star is the complex of this. Okay, so in this, the real part of xk, just take this bracket, the real part xk should be equals to the real part of x minus k will be there, n. Okay, and similarly, the imaginary part of xk should be equals to minus of imaginary part of x k must be there. Okay, so similarly the magnitude of x k, this should be equals to what? Magnitude of x minus k okay, and this is the magnitude. So there are two things in that, one is the magnitude and second is the angle. So angle of this angle of this minus k, okay, this should be equals to minus of angle of x minus k. Okay, so this is simply the linearity of discrete Fourier transform, in which you can say that xk should be equals to the x star, means the complex of x minus k for any value n, in which the real part and the imaginary part we have defined over here. Okay, this in the similar way. So there are the two things in that. One is if you are going to take the magnitude, and second is the angle. So we have taken the magnitude and the angle. So this is the simply the symmetry. Okay, next move forward. Second we take is that linearity. Linearity. So in the linearity, simply a x1 of n, okay, plus some constant b x2 of n. If you are going to take the discrete Fourier transform of this, what should it will become? A capital X1 k, okay, plus b capital X2 k, okay, where a are constant on both the side, b and b are the constant on both the side. There is some simply, you know that the what is the discrete Fourier transform of x1? It is capital X1 k, and discrete Fourier transform of x2 is simply this. So it is following the concept of linearity. Okay, so let's move forward, where the third thing is circular time shift. Circular time shift, okay, in which simply x n minus m, there is a time shift. N is simply the previously it was xn, but there is a shift of m. Okay, so this can be written as for any value of n. So discrete Fourier transform of the circular time shift should be, if you are going to take the discrete Fourier transform, it should become w capital N for any value of n to the power k into m xk. We have already studied that how this w capital W is coming in the last lecture. Okay, so here you can understand that how the this property, this thing is simply known as the circular time shift. Okay, next is the circular convolution is there. Circular convolution. Okay, so circular convolution can be written as simply summation m is equals to 0 to capital N minus 1. Okay, one is x1 m, and second thing is x2 n minus m, okay, for any value of n. This the discrete Fourier transform of this will become what? x1 k and x2 k. Okay, so this is a circular convolution. So circular convolution between two n point signal is sometimes denoted like you can write down here, circular convolution between two n point signals is sometime denoted by like it can be denoted by you have already studied about the remember this, we write down the convolution right like this, x1n with xn. Okay, so this is a circular convolution. Now next is modulation. Modulation. Now how the modulation can be written as, one signal is x1n, second is x2n. You are going to take the discrete Fourier transform of this, then it will become 1 upon n summation of something L is equals to 0 to n minus 1, in which this x1 L into x2 k minus L for some value n. Okay, so these are some of these properties the properties like linearity are very easy to prove. Okay, but the properties involving the time shifts can be quite confusing. Okay, notationally, but otherwise these are simple. So just let's take just an example. So consider a 4-point discrete Fourier transform form. Okay, consider the 4-point discrete Fourier transform. Okay, so in this you can see that in this xk this is simply equals to what? N is equals to 0 to 3 xn w 4 k n. Okay, so you can see from here that n, the value of n is from 0 to 3. Okay, of the this is of the length 4, of the length 4 signal xn. Okay, so this can be written as, we can write down the discrete Fourier transform of this as xk, in if you are going to extend this, can be written as x0 if there is 0 from 0 to 3. Okay, so 0 w 4 0 k. Okay, 0 k, because first we have taken n is equals to 0 plus x 1 w 4 1 k plus x 2 w 4 2 k plus x 3 w 4 3 k. Okay, like this. Now you can see that the product w4 1 k x k can be written as if you are going to write in the product w4 1 k into xk can be written as how it can be written? w4 1 k xk, this should become what? If you are just going to multiply this, so if we multiply, this will become what? This will become x0 base same power should get plus w4, it will become 1k. Okay, plus x1, this will become w4 2k, x2 it will become w4 3k plus x3 it will become w4 4k. Okay, so we can rewrite this as it will become x3 w4 0k, because w4 4k this can also be equals to w4 0k. This can be proved. Okay, so this can be written as, we have just shifted this on this side, plus it will become x 0 w4 1k plus x 1 w4 2k plus x 2 w4 3k. Okay, so since w4 4k is equals to w4 0k, so this can be seen that the discrete Fourier transform of the above sequence, what is this? The sequence is simply x3 is there, then x0 is coming, now then x1 is coming, then x2 is coming. Okay, this sequence will become like this, which is precisely the sequence xn. This is the sequence simply xn circularly shifted to one sample by one sample. This is circularly shifted by वन सैंपल, ओके, एक सैंपल इसको शिफ्ट कर दिया करो. दिस प्रूव्स दैट द टाइम शिफ्ट प्रॉपर्टी फॉर अ शिफ्ट ऑफ लेंथ 1. दिस प्रूव्स टाइम शिफ्ट property for a shift of length 1. Okay, so in general, if you are going to multiply uh, the discrete Fourier transform, if you are going to multiply the discrete Fourier transform of a sequence of W and Km in an n point circular shaft, in an n point circular shift of the sequence by m samples, the convolution properties can be similarly demonstrated. All right, so we can also see the convolution properties. How? Let us see. So it is useful to note that the circularly shifted signal x n minus m, capital N, is the same as linearly shifted signal x bar, okay, n minus m. Okay, so where x bar n is the n point periodic extension of xn. Okay, so it's easy to understand. Now let's see. Now you can see this in this it is shown that this is the signal xn. Okay, so for the signal xn we have taken that x bar, and this is we have already shown in the last lecture. So if we are going to make the shift, okay, if you are going to make the linearly shifted signal, then x n minus n m should become like this. Okay, there is a shift of m over here, and similarly you can see this, that the circular shifted signal should also be very similar to the linearly shifted signal. You can see this, that we have the sequence like this from 0 to n, and for xn we have like this. Okay, on the right left of from 0 to n we have this. So we have made a linearly shift of m. So we have made a linearly shift of m, then this signal has shifted, these two signals have shifted on the right side. Okay, so these 2 points have shifted on the right side. So it is you can see that now here 0 is here. Okay, here, and this the linearly shifted signal is very similar to the circularly shifted signal, as we have already told you that the linearly shifted signal is very similar to the circularly shifted signal. Okay, so you can see in this diagram.